Hi everyone. Titration of a weak acid, find pKa. It's actually very simple if you know the trick, right? Do you remember the trick? All right, let's talk about the trick. So now I'll throw up a nicer picture, okay, nice titration plot from the notes, okay? And as you can see, it doesn't matter if you've got a strong acid or weak acid when titrated, okay, and I'll probably do a bad picture myself here, okay. So for a strong, as you saw in the picture, halfway up the strong acid, strong base titration curve is equivalence, right? That's the equivalence point where acid, moles of acid equals moles of base, yeah, fair enough. However, the weak acid, there's a buffering region, and then we kind of go like that. Now it's the buffering region, right? Buffer, yeah, okay. However, the equivalence point is the same, okay? So the question is then, well, how do I, with this weird aligned shape, how do I identify the equivalence point? Well, it's kind of interesting because at that point there, we get a point of inflection. It's kind of like when an INI turns to an outie, convex concave, yeah, okay. Now, that's, obviously pH up the side there. If we actually did the derivative or double derivative of pH, we'd actually get a spike, okay, at that particular volume. And that's the trick, okay? So we're going to use the computer to hit the target. That sounds a bit familiar.
That's impossible, even for a computer.
Okay, I have to excuse my nerdiness, right? Okay, so we'll use the computer. It will tell us, and we just slip back into the pictures here, okay? And there they are, right? So there's your kind of standard plot, yeah, okay? There's kind of like the strong acid plot underneath, which it would be, right? Okay, so this is your weak acid plot. That's the equivalence point. That's when we change to an INI to an outie. Okay, so it's about 10, isn't it, right? If we look at the derivative, or even the second derivative, we get like a burst or a spike, right? And that allows us to pinpoint extremely accurately the volume. Maybe it's 10.2 milliliters or something, right? Okay, so we had 10.2 milliliters of NaOH. We see the equivalence point as a spike in the derivative pH, yeah? Okay, so that's kind of hard to see by eye. That's easy to see with the computer, okay? As is the double derivative. Doesn't matter which one you use. Then you say, well, hey, what's the big trick? pH equals pKa at half equivalence, right? So if I know the equivalence is at 10.2 milliliters, half equivalence is half that, 5.1 milliliters. Ah, fantastic. So you can kind of, read back over, get exactly half the distance, read across, and the pH equals the pKa for the weak acid at half equivalence, yeah? So that's full equivalence, half equivalence, just do it in terms of milliliters of titrant, yeah? And then just read across. Now you can, go by eye and read across on the graph, but if you look in the data set, right, so I can find a good one, right, There's a data set. You can actually, look at the numbers in the data set. Oh, there's a better one. So if say it was 10.5, go back to 5.2, and it's, there's the pH, right? You can use the data points probably a little better if the points are close together. You may better get a better idea just by doing it by eye. But the bottom line is you can find the pH at half equivalence. That's the pKa, and that's the goal of the experiment, okay? So you do it for practice, and then part 2, you'll do it for an unknown, and I'll grade you on how well you get the unknown value. Okay, hopefully that makes sense. Any questions, water cooler or discussion, also office hour, don't forget, on Thursdays. Okay, see you next time.